The composite design pattern is a structural design pattern that enables the creation of tree-like structures to represent collections of objects, where both individual objects and groups of objects are treated in a unified manner. So to understand what this means, let's create a scenario, then code up a simple naive solution, then fix it with the composite pattern. So let's say that we get an Amazon delivery of a large package that contains multiple items. So as you can see, the boxes can contain groups of other boxes and items, and the above this diagram shows how a package of items can be represented as a tree structure. So at the top we have the big main Amazon box that you would receive, and then within this box we have two more smaller boxes, and then within this smaller box we have a microphone, so our first item that we open, and then the second box contains two smaller boxes, and this box contains a mouse and this box contains a keyboard. Okay, and you can see that this is represented as a sort of tree structure. So say that we need to find the total price of the items within any package. So for example, the total price of all the items in this top main package would be the cost of the microphone plus the mouse plus the keyboard, whereas the price of the items within this package would be just the mouse or the keyboard, and the total price within here would be the keyboard. The total price of this package is the mouse. Okay, so the solution that naturally pops into the head is to create an array of boxes and items, then loop through them recursively to find the total price of the package. So here is the simple solution. So we can see here that we've created a keyboard class with a price, a microphone class with a price, and a mouse class with a price. We can then have a box, which is just a list of any type of object, and we call this items. And within this box class we have a method for adding an item, and we just add it to the list of items. And then we have a calculate total price class, which first of all has a field called total price, which we set to 0. It loops through all of the items in the items list, and it checks what type of object the item is. So if item is a keyboard, then we cast the item to a keyboard object, which means that we can then access its price field. Okay, then we have to do the same for mouse. We cast it to a mouse and access the price field on the mouse class, add it to total price, and then we do the same for microphone. Else if the item is a box, then we cast the item to a box and call calculate total price. So we're calling this method recursively. Then we just return the total price of the box. So you can see that this method is ugly because we're having to check the type of object and then cast the object to that type to be able to access its price field. So this is very ugly solution. First of all, it's very hard to read. This method is already bloated with just 3 types of items. So the more items we add, it's going to become even more bloated. And if we add more items or remove items, then we have to modify this class, breaking the open-closed principle. So if we use this solution to create the package demonstrated in the previous tree diagram, we can see here that we first of all create the big package to deliver containing box 1 and box 2, and then box 1 contains a microphone, box 2 contains box 3 and 4, and then box 3 contains a mouse, box 4 contains a keyboard, and then we're just adding the boxes to the correct box and adding the packages to the correct boxes, and then we can call calculate total price. So you can see that this solution calculates total price correctly, but it has some obvious flaws that we have already discussed. So we have lots of conditionals, which is very hard to read, and we're violating the open close principle because whenever we add a new item, we have to modify the box class. Whenever we have lots of conditionals that are checking the type of an object and casting it to another object type, it's often a good sign that we need to use polymorphism. And we can use polymorphism by creating an interface called item and extracting common methods or logic between the objects into that interface, like so. So here we have an item interface with a getPrice method, and we can see that both box and each of the product objects or classes are extending this item interface, meaning that they will all have this getPrice method. So a box is essentially composed of a group of items. So you can see here this is represented by the diamond arrow, and you can see this field here, a box is composed of a group of items, but a box is also an item itself, represented by the arrow. So a box is simply just a group of items, but a box and its contents can be treated the same way as items, thanks to polymorphism. So now let's go ahead and create the code solution. Okay, so I've created a new folder for our structural design patterns, and in here I've created a composite folder for this example. So first of all, let's create an interface called item. And items are going to have a single method called getPrice, which returns a float. And we can now create our specific item classes. So first of all, let's create a keyboard class. And this needs to implement the item interface. So each class will need to have a field to store its price. So let's go ahead and create a private float called price. And I'm just going to set this for now as a constant. In a real application, it would be much more sensible to create a setter method for this, or set the price in the constructor. But for now, we're just going to hard code a value in for the price. And then within this getPrice method, we need to return the price. Okay, so let's now go ahead and create our other items. So we're going to need to create a microphone. And this needs to implement the item interface. And again, we're going to have a private float for the price. And again, let's just hard code this in for now. And we just return the price. Okay, let's create our mouse class. And I'm actually just going to copy and paste this in to save some time, as it follows the exact same structure as we have with our keyboard and microphone. Okay, so now let's create our box class. And a box, remember, is just a sort of class that stores a group of items. And a box is also an item itself, so let's implement the item interface. And now a box needs to actually have a field for storing a list of items. Okay, let's also provide a method for adding items to the list. Okay, now we need to implement the getPrice method. So what we're going to do is we're going to loop through the items in this items list, and we're going to add it to a total variable. So let's create a float called total, and then we're going to loop through each item in the items list, and we're just going to add it to the total. And here we can call item.getPrice. Okay, and we know that each item is going to have a getPrice method because all items are implementing this item interface. So we no longer need to check the type of item object. We can just treat them all as items, and here we are basically using polymorphism because this item object can take many forms. It can be a keyboard, it can be a microphone, or it can be just another box. Okay, so polymorphism is allowing us to giving us a lot of flexibility here. And then at the end we just need to return this total. So let's now actually use this solution in our program.cs file. And what I'm going to do is, rather than code all of this out, it's a pretty hefty bit of code, so we're just creating the tree structure that we had beforehand basically. So what I'm going to do is just copy and paste this all in, and then let's actually import the correct namespace. So it is this one. Okay, so this all looks okay. So just to remind you of the tree structure that we are creating here, let's see if I go over here. So if I just scroll up, so we're essentially creating this tree structure. So we have one big package that contains two boxes, then box 1 contains a microphone, box 2 contains two more boxes, and then we have a mouse and a keyboard. Okay, so that is what we have there. And let's see, so let me go back over here. Okay, so let's run this file to see what we get. And I think actually we've messed up the copy and paste in here, so let me just copy and paste this in. Okay, so that should hopefully be correct. And the total price of the package is $87.99. So if we quickly check what we have in the packages, we have a keyboard, a mouse, and a microphone. So we have 40 plus 29, which is $69.99, and then we have a mouse, so that's $87.99. So the total price of the package has been calculated correctly. Okay, perfect. So you can see that there has been no change in the way that the client would actually use this solution compared to what we had beforehand. The biggest change in using this solution is that it calculates the price, is in the way it calculates the price using the getPrice methods, because we can now treat all objects in the box in the same way, as they all implement the item interface. And this means that we don't need conditionals to check the type of each item. And this satisfies the open-close principle, as our code is open for extension but closed for modification. So we can create a new item class, extending our code without needing to open any existing classes for modification. So here is the Gang of 4 UML for the composite pattern. So you can see that we have our component interface at the top, and then we have our composite class. So a composite meaning that it contains sort of multiple components. So you can see here that a composite has some children, or it contains some other components. So it has a list of components, and then it has a method for adding components to the list, and it also has an execute method to execute some sort of logic. And then we have our leaves, which are the sort of individual products themselves. Okay, so the composite pattern is useful for representing tree structures, for example folders and files, and we can see here that a folder is like a composite. It contains either other folders or individual files, and you can see here this folder contains 2 files as well as another folder which contains 3 files. And the composite pattern is very useful for representing these kinds of tree structures. And another example is a graphical editor that allows you to group shapes together and group groups of shapes together as well. So when you drag a group, all shapes should move together in the same way. So you can see here we have a group which contains a circle, triangle and another group, and this group contains two groups, and this group contains two squares, and this group contains two circles. Okay, so you can see that this can be represented as a tree structure, and this is where you might start thinking that the composite pattern could be a good way to represent this in code.